Okay, so everyone, uh, let's start this event of PASCOS 2021. Unfortunately, this year, PASCOS can't be held offline due to this pandemic situation. So we go fully online for the first time of the PASCOS. Well, we hopefully next year that everything goes as usual, so we can meet face to face. Anyway, this year we have a great speaker and physicist, Professor Hitoshi Murayama, as our public talk lecturer in PASCOS 2021. Hitoshi Murayama is a professor of UC Berkeley and also founder of the Kavli Institute for Physics and Mathematics of the Universe, so-called IPMU in University of Tokyo. And he was the first director. And he did not just high energy theory, he did cosmology, even for the high energy experiment. And also I heard you wrote some paper on condensed matter physics too.
Yeah, some of them, yeah.
Right, so he basically do a lot of different things, and he knows a lot of interesting ideas of the physics or even outside of physics too. So it will be really interesting lecture, we hope. Okay, now, are you ready?
Yeah, I'm ready.
Okay.
So can I share the screen?
Yep, please.
Okay, here we go. Now I hope things are working full screen.
Yeah.
Okay, thanks for the introduction. So I'm Hitoshi Murayama from Berkeley, California, as well as Tokyo. And I'm giving this talk today for general public titled Quantum Universe. And the title meant to be something that contradicts with each other. Universe is the biggest thing we can observe, of course. But quantum has to do with something very small. But somehow small things and the biggest things are connected to each other. And that becomes actually one of the main themes of my talk today. And as well you mentioned, I'm actually one of the attendees of this international conference called PASCOS. And PASCOS stands for the International Symposium on Particles, Strings, and Cosmology. So hundreds of physicists gather around from around the world every year and talk about exciting research that's happening at the intersection of particles, strings, and cosmology. So everything is online this year. So I'm giving this public lecture also online. But nonetheless, this is an exciting meeting for many of us working on physics. And many of people might think that the physics is something very difficult to understand. We'd rather not come close to it. But what we physicists do is to ask really simple but profound questions. And these questions are so profound and actually interesting. So I hope that many of you actually share these questions as well. Because the questions we ask, it's just like a little kid watching the night sky with awe. And we actually start to think about some of these really profound questions like, how does big universe begin? Where it's going? What is its fate? What is it made of? And what are its basic laws? And where do we come from? Why do we exist in the universe? And one of the themes of my talk today is with the last question, where do we come from? But that actually turns out to be related to many of the other questions on this list too. So these are the questions we physicists attending this PASCOS meeting would like to understand. And of course, these questions had been talked about for millennia in the history of the humankind. For example, in the context of religions or philosophy. Only towards the end of the 19th century or so, we started to ask this question, where do you come from a scientific approach, like in the context of evolution. And I'm not totally convinced that evolution is going the right way these days. But anyway, this became a scientific question towards the end of the 19th century. And this question is now getting in more and more interesting. And to understand where you come from and the kind of machine you need for this research is, of course, this one, the time machine. And unfortunately, we don't have this kind of time machine, but we can rely on some other kinds of time machines in our scientific research. And one of them is the giant telescopes. So this telescope is a picture of the Subaru telescope Japanese astronomers built in the big island of Hawaii atop the Mauna Kea. The mirror itself has an incredible large size of 8.2 diameter mirror. So with this kind of big mirror, you can collect a lot of light so that you can observe very dim things, which are far away. So using these giant telescopes, you can look farther and farther away. And if you're looking at the galaxies millions of light years away, the light would take millions of years to reach us. So you're actually looking back into the past by a million years. So that's why the giant telescopes work like a time machine. And another kind of time machine I'm going to talk about later is called particle accelerators. And I come back and talk about this later, as I said. So let's leave that for the moment. But let's just think a little bit about what these giant telescopes actually do for us. For example, this is a picture of the Andromeda galaxy we took with a new camera on the Subaru telescope. And Andromeda galaxy is 2.3 million light years away from us. So for light, it takes 2,300,000 light years to reach from Andromeda to us. So what that means is that if there's an alien living in Andromeda and point their telescope at our planet Earth and trying to see how we might look like, what they're going to see is the human beings are like this one, because what they see is the way we were 2 million years ago. So this is what I mean. When you look far away, you're literally looking back into the past. This beautiful picture is the picture of what is called the cluster of galaxies. Something like 100 galaxies are living together in this picture. And this one happens to be about 2 billion light years away from us. So if there's an alien living in this cluster of galaxies and point a telescope at our planet, the way we will look to them is that like this one. So singular cellular organisms. This is the way we were 2 billion years ago. And this slide is about one of the distant ever galaxies we ever observed. So this is a picture taken by the Hubble Space Telescope. And if you blow up this square, then you see this picture. If you further blow up this square, you see this little red smudge. And this little red smudge actually turns out to be a full-blown galaxy of something like 100 billion stars in it. And this particular galaxy happens to be 13.3 billion light years away from us. So if they were an alien in this galaxy and point their telescope at our planet Earth, and what they're going to see is nothing, because our solar system wasn't born back then. So our solar system is believed to have been born about 4.5 billion years ago. So 13.3 billion years ago, our solar system didn't exist. So these aliens would see nothing. So that's the idea. If you look far away, then you can look back into the past. And now we believe that the universe was actually born 13.8 billion years ago. So if you work very hard, build a telescope, and look away over 13.8 billion light years, then you're supposed to be able to see the beginning of the universe. Namely, you should see the Big Bang. And in fact, here it is. This is the picture of the Big Bang. So this satellite launched by European Space Agency called Planck took the picture of the Big Bang by looking 13.8 billion light years away from us, so that you can look back 13.8 billion years ago. And then this satellite could take a picture of the baby universe. And that's the picture you are seeing here. And of course, this satellite would look at all possible directions. So everything's supposed to look like a big beach ball. But this picture here is that you stretch out the surface of the beach ball and try to fit on the surface of the slide. That's why it looks kind of an ellipse. But it is actually meant to be basically like a beach ball. And it's also extremely exaggerated. So what you see in orange is the slightly warm spots. What you see in blue is slightly cold spots. But the difference in temperatures is really, really slight. They vary only by 1 part in 100,000. So if you think of this as, for example, the ocean wave, living on the ocean that is as deep as 100 meters, for example, then the change in the temperature is something like a ripple only by a millimeter tall wave sitting on this ocean of 100-meter depth. So this variation is really tiny. So it turns out the universe started out pretty bland and uninteresting and boring because everywhere looked the same. But it turns out that this tiny variation of temperatures turned out to be very important later on. So please remember that there was this tiny variation of temperatures at the very beginning of the universe that actually turned out to be the source of us at the end of the day. Now, I told you that this is the picture of the Big Bang, which is true, that you are seeing actually the way the universe was when it was very small and hot. But it turns out that this is actually not the Big Bang, not the beginning of the universe. What you're looking at here is actually the surface of the Big Bang. Because the way you understand this picture is sort of like when you look at the sun, and don't do that because that would burn your retina. But suppose you did, then all you can see is the surface of the sun. And that's because the sun is a ball of very hot and dense gas inside, and light can't go through it, so you don't see the center of the sun. The only thing you see, the surface of the sun. So Big Bang is the same way. By trying to look as far away as possible so that you can hope to see as far back in the past as possible, trying to get a glimpse of the very beginning of the universe, at some point, universe becomes so small, so hot, and so dense, just like the sun, the light can't get through it anymore, so you don't see beyond this. So this is actually the surface of the Big Bang, not the Big Bang itself. So it turns out that if you use any kind of telescopes whatever, you can never ever see beyond the surface of the Big Bang. You can never observe the Big Bang, the beginning of the universe, directly. So that's kind of sad, sad news, isn't it? But of course, we're physicists. We're trying to go beyond this problem. So the picture of the Big Bang you saw is actually coming from here when the universe was only 380,000 years old. So of course, 380 years is a long time for us, but for the universe that is 13.8 billion years old, this is actually a baby universe when it was sort of crying like a baby. So we actually managed to take the picture of the baby universe. That's an incredible technological achievement which humankind has made to accomplish. But at the same time, we still do want to understand what was going on at the very beginning of the universe. 13.8 years later, you were thinking about where you came from. So because any telescope cannot see anything beyond the surface of the Big Bang, you would never learn what's going on at the earliest moments of the universe using telescopes. So that's the sad news. But the good news is that there's another way of studying the beginning of the universe using the other time machine I mentioned earlier, namely the particle accelerators. So what these accelerators do is to try to recreate the Big Bang. You try to do the early universe in the laboratory. For example, using these particle accelerators, you can study the way the universe was when it was only 3 minutes old. So when the universe was only 3 minutes old, it was such a scorching hot universe. Everything was moving very, very fast, and nothing could actually stay together. The atoms get broken apart, atomic nuclei get broken apart, and protons and neutrons are flying apart, zooming around in the universe. So it was really, really hot. But as the universe got bigger and started to cool down a little bit, these particles start to move a little bit slowly, like neutrons and protons. And the way they move is something you can study in the laboratory too. You basically throw protons and neutrons against each other in the laboratory using these particle accelerators. Then you can observe that once in a while, they will stick with each other. Then what used to be these independent neutrons and protons now form helium nucleus. So this is the way we believe the helium in your balloon at birthday parties were actually made. And because you can study this process in the laboratory, you know how frequently they can stick with each other and make a prediction that in the whole universe, hydrogen to helium ratio is about 3:1. And you can go out and observe the gas of hydrogen and helium in the universe today. And it turns out that the ratio is indeed 3:1. So that's how we believe that we actually do understand how the universe was like when it was only like a 2 to 3 minutes old, because you can redo it in the laboratory using particle accelerators. So that's the best we know at this moment about the earliest moments of the universe. by comparing what you can do in the laboratory using accelerators and what you can observe in the universe using telescopes. But now I'd like to tell you one story about how we might be able to go beyond this to approach the moment when the universe was even younger than a billionth of a second. And that story has to do with dark matter. So one thing we know is that we are living in the Milky Way galaxy. And in the long past, people used to fight over where a planet Earth is the center of the universe, or the sun was the center of the universe, and people were literally killing each other. But it turns out that both of them are wrong. Our sun is actually in the suburb of our Milky Way galaxy, not at the center. So being in a suburb, about 28,000 light years away from the center of the galaxy, our sun actually has to revolve inside this Milky Way galaxy. And we're actually moving pretty fast. Our solar system revolves at this whopping speed of 220 kilometers per second. But if the sun is moving so fast, why doesn't it just zoom out from the galaxy in a moment? Something must be pulling us so that we can stay comfortably inside this galaxy. But what exactly is pulling us? And of course, inside the galaxy, you see about 100 billion stars, and stars exert gravity on us. So perhaps they are pulling us and keep us inside the galaxy. But you can observe stars in the telescope, you can count them up, and estimate how much gravity they can exert on the solar system. And that turns out to be nearly not enough. So if you think that our Milky Way galaxy is a collection of stars, then the gravity coming from all these stars combined turn out not enough to keep our solar system inside. So our solar system should have wandered out of a galaxy almost 40 billion years ago and be wandering in the empty space now, today. But clearly that's not what we're doing now. So what that means is that there is actually more gravity than meets the eye. So in addition to all these 100 billion stars we can observe in the telescope, there must be a lot more mass inside the galaxy that would give us gravitational pull so that even though we're moving so fast, we can stay inside the galaxy. And that's something that doesn't show up in telescopes, but nonetheless pulling us inside the galaxy is what we call the dark matter. It's dark because we don't see it, but it's matter because that actually exerts gravity on us. So after this kind of research, we learned that the true nature of galaxies is not the collection of stars. It is actually an island of dark matter. And inside this island, you sprinkle in just a few stars in there as a minority of this galaxy. And the stars may stretch out over maybe 100,000 light years or so, but dark matter would stretch out this long tail going over a million light years and beyond. And so this is actually the true nature of galaxies. So there's a lot more than meets the eye. So that's the dark matter. And if you actually study this more carefully, not only you see the evidence of dark matter in our Milky Way galaxy, but many, many other galaxies as well. And also in the cluster of galaxies I mentioned earlier. So in this picture, all these round, beautiful yellow objects are galaxies, each one of them with about 100 billion stars in them. So they're all beautifully shaped round objects. But if you watch this picture for a while, you start to notice there's something that looks really, really stretched out. For example, here, you see something is really stretched out. Here too. Here's another one. Here's yet another one. You see something over here too, over there, over there. Here's another one. Here's another one over here, and also this one here and there as well. And here's the last one. So what are they? What are these really stretched out things? And by studying them, you can tell that they are galaxies. But galaxies are supposed to be round. As I also told you, the stars are moving inside galaxies. So if there were a galaxy of this stretched out shape, because the stars inside are moving, those galaxies will spread out and break apart almost instantly. But apparently they are together. So it turns out that this stretched out object, you see many of these in the picture, are actually regular shaped galaxies similar to any one of these. But it turns out that this cluster of galaxies, where hundreds of galaxies are living together in a little village, would actually fool us to make the galaxies look like they are stretched out. And that's actually a trick played by dark matter living in this cluster of galaxies. So here's the idea. So this is the cluster of galaxies, which is filled with dark matter, and that's why there's a strong gravity around it. And just imagine that from our point of view, there's another galaxy beyond this cluster of galaxies. Basically, it's behind that. And when the light from this faraway galaxy reaches us, because of strong gravity on its way, the light actually falls due to gravity, namely that it bends. So this cluster of galaxies then acts like a magnifying glass. So light bends. And you might have an experience that if you look at the edge of the magnifying glass, the letters of the book you try to read may look very stretched out, and you don't, they are actually not readable. So in a similar way, the image of this regular round galaxy on the edge of this magnifying lens may look really, really stretched out. And that's exactly what you saw on the previous slide. So just get an idea better on what's going on here. Just imagine that there are a bunch of galaxies far away behind this cluster of galaxies flowing like river. But if one of the galaxies comes almost exactly behind along the line of this cluster of galaxies, then they start to look all stretched out. But of course, nothing would happen in this galaxy really, because this galaxy is really, really far away. This cluster of galaxies is much closer to us. So this stays the regularly shaped galaxy. Nothing's happened to them, but they do look stretched out. But after they move beyond and away from this cluster of galaxies, they go back to the regular shapes. And that's what you see in this computer animation. So when the galaxy is right behind this cluster of galaxies, they look really, really stretched out like this one. But after a while, they flow like a river and eventually move away from the shadow of this cluster of galaxies and return to the normal shapes. So now you can see that this is really just a trick played by dark matter in this cluster of galaxies. So that's also true in this picture too. So this is a picture taken by the Subaru telescope I mentioned earlier at the beginning of my talk. And what you see, these bright shiny objects are nearby stars that is saturating your camera. So forget about these things for the moment. What you're really interested in this picture is these little dots. And each little dot is actually a galaxy, some tens of billions of light years away from us. But with a modern technology, you can actually observe the shape of these galaxies, tens of millions of billions of light years from us. And you can tell that they are actually not regular shape. They are slightly stretched out. So what that means is that there must be the ocean of dark matter in front of those galaxies so that light got bent on their way before reaching us. Namely, the dark matter is playing tricks on us. But if you know there are tricks being played, then you can tell where the tricksters are, namely where and how much dark matter there is between these faraway galaxies and us. Then you can start making maps of dark matter. So that's incredible. You don't see dark matter directly, but you know exactly where they are and how much of that there is by creating the maps of this dark matter using this gravitational lensing effect, because the gravity from dark matter acts like the magnifying glass. So by studying these shapes, people could figure out that more than 80% of matter in the universe today is not made of atoms, but something totally different. How do we know that? That's partly because of a beautiful picture like this one. So this is a beautiful picture, but you should be glad that you're not there. So this is the picture of two clusters of galaxies. Here you see one of them, a pair of pink and blue. Here's another cluster of galaxies, that's another pair of pink and blue. And these clusters of galaxies are 4 billion light years away from us. One thing which is funny about this picture, though, is that what's shown in pink is the regular gas made of atoms, which became so hot, up to like 1,000,000 degrees, so that it's lighting up with X-ray. On the other hand, what's shown in blue here is where the dark matter is, because they play tricks on us, then we could figure out where the tricksters are. So this is the set of gas and dark matter. But I told you a few minutes ago that everything is held together by gravitational pull of dark matter, including our solar system. But this gas is not together with dark matter for some reason. And also in the other cluster of galaxies, the gas is not together with dark matter either. So it turns out that what happened here is that this is an aftermath of a head-on collision of two clusters of galaxies at an incredible speed of 4,500 kilometers per second. And here's a computer simulation of this. So each of the cluster of galaxies is again an ocean of dark matter, but you sprinkle some atomic gas in them. And when they collide, atoms would scatter against each other. They get heated up. There's a friction. They slow down. But dark matter keeps moving as if nothing has happened. And then the gas that got slowed down by the friction is being dragged by the gravitational pull from this dark matter that is moving forward in front of them. So that's how you can actually understand this picture. So what you learn from this picture is that, first of all, atoms would interact with each other, and we knew that. But at the same time, atoms and dark matter don't seem to interact at all. They seem to have passed each other without any problems. And also dark matter doesn't seem to interact with dark matter itself because they seem to have passed each other without any problems. So dark matter is the essential element of the cluster of galaxies, but they're very spooky, ghost-like objects, and they look kind of evil to us. But it turns out dark matter is not evil at all, because dark matter is actually our mom. So I showed this picture of the Big Bang, where temperatures varied only so slightly from one place to another. But when the temperature is slightly hotter, there's a little bit more dark matter, and pulls more stuff in due to the force of gravity, becomes denser, then gravity becomes even more strong, pulls more stuff in, becomes even more dense, gravity becomes even more strong, pulls more stuff in there, and eventually you have this contrast between dense spots and the empty spots. And in these dense spots, the force of gravity pulls in also ordinary gas too, made of atoms. But as you saw in a previous slide, gas would interact with each other. They would emit light and cools and collapses down to form stars and galaxies, and eventually us. So that's how you can recreate the universe in a computer run by Naoki Yoshida in this simulation, one of my colleagues. But if you actually simulate a wrong kind of universe that doesn't have dark matter in it, even 13.8 billion years later, there's nothing. There's no contrast. There wouldn't be any stars or galaxies, and not us. So that's what I meant, that dark matter is a mom. We were born thanks to the gravitational pull of dark matter. But nobody knows what dark matter is. Nobody has met her. So that's actually one of the things we really would like to do. We would like to meet our mom and thank her to letting birth to us. And that's the role of dark matter. So using this idea that dark matter's gravity acts like the magnifying glass, our team created the largest 3D map of dark matter ever. So this is actually 1 billion light years sideways and quarter billion light years vertically and 8 billion light years deep. And you see the contours of where dark matter is dense or is empty of dark matter. And if you compare this 3D map of dark matter and 3D map of galaxies, you can tell that where dark matter is, you find galaxies. Where dark matter is, you can find galaxies. So this is already a proof that the galaxies were born out of the gravitational pull of dark matter. So dark matter is really our mom. So to summarize what I talked about already so far, I'd like to show you the video done by George Smoot. He's one of my colleagues in University of California, Berkeley. He got a Nobel Prize for taking the picture of the Big Bang for the first time ever back in the 90s. And after he got a Nobel Prize, he was asked by University of Generation to do something interesting with students. And he decided to reenact the Big Bang with the marching band for the football team of UC Berkeley. So let me run this for you.
I really admired the band. And so when they said we wanted to react to the Big Bang with the guys from your lab, I said, no way, I want the band. Okay, so now I got to tell you what the Big Bang is so you guys can do this before the sun goes down. Okay, so the idea is everything in the early universe was packed together very densely. It may have gone for infinite. We don't have infinite people, so we just have to use what we got. And everything stretched, right? Everything got bigger. And the further away you are, the faster you go. So we're going to want to start at the beginning with everybody packed dense and jostling around and playing high tempo rapid.
Okay, here's the big band.
Then at the mark,
People running like
moves
crazy.
apart. The people on the outside moving faster than the people on the inside.
The universe is getting bigger.
And there's a little bit of irregular motion. So
this irregular motion
steps.
is important.
Okay. I know you can do this. Right? And then what happens is you're going to coalesce together in groups of 6. Right? So you have to find 6 buddies. And half of you are going to form spiral galaxies. 3 people facing one way, 3 the other, and you rotate slowly as you move out. And the other half form elliptical galaxies, which are round blobs that keep moving out. Okay. So
here's a spiral galaxy.
There's a brass section out there called tubas. They make a really spectacular spiral galaxies, a really big one, like our own galaxy or like Andromeda. So you guys get to be near the middle, and you get to make a really cool, you don't have to run out so fast, but you get to be able to orient where half is facing the other way, and you get to rotate with a sort of twist up. And you're like the centerpiece of this whole thing. Go tubas. Great, guys.
All right. And this is how we were born. And remember, 80% of people here are dark matter. You don't get to see them. And George himself is sitting at the center of a Milky Way galaxy, he said. So he happens to be actually a supermassive black hole that is 4 million times heavier than our own sun. So that might actually remind you something. So people observed the center of this galaxy called M87 by using a combination of the radio telescope around the world. So in this picture, you see this incredible high energy, high speed gas coming up from the center of the galaxy called jet. And people believe that this jet must have been caused by something monstrous at the center of the galaxy. The only monstrous thing people think of is a supermassive black hole, like George was in that video. And to observe this supermassive black hole, people work together to connect all of these radio telescopes around our planet. And what we learn in school for every physicist, that if the telescope is bigger, you can resolve smaller things. So if you make a telescope as big as a planet, you can really see tiny things. And that's what they did, and they could take a picture of the black hole. So inside this picture, this range is the photon, even light, gets trapped by the gravitational force of the black hole, that it could never come out. That's why it looks dark. The size of the black hole itself is slightly smaller. That's the size of what is called the event horizon. But anyway, this is the famous picture of the black hole, which now you could tell that this big black hole is 6.5 billion times the mass of the sun. But if I tell you that, okay, now I know what dark matter is. This is the invisible mass that is keeping us inside the galaxy, but not so fast, because this M87 galaxy as a whole weighs whopping 2 trillion suns. And what I was telling you is that gravity comes from 2 trillion suns. It's not nearly enough to keep the stars inside. So 6.5 billion is nowhere close to enough. So black holes are there, but they are not pulling us inside the galaxy, and therefore they are not the dark matter. So what could it be? We have learned it's not atoms, it's not dark stars, it's not even black holes, it's not neutrinos either. So everything we know actually doesn't work. So it's got to be something totally different, and we don't know what that is yet. That's why I told you we haven't met our mom yet. And one of the best ideas a lot of people at this conference talked about is the idea called WIMPs. So they are actually tiny, tiny elementary particles. They can punch through our planet without any problems because they're so shy. They don't interact very much. And the WIMP stands for weakly interacting massive particles. So the idea is that they are stable, heavy particles produced in the outer universe, and they are left over from near complete annihilation, and they are around us still today. If that's true, maybe we can make them too. maybe we can make the dark matter ourselves. And that's an experiment that is ongoing in Europe. So this picture shows the border region between the Switzerland in front and France beyond. This is the size of the Geneva airport, that's a runway. And what's painted on this aerial photograph is the location of the underground tunnel that's about 100 meters deep. And the circumference is something like 27 kilometers long. And inside this tunnel, you circulate the beams of tiny particles called protons one way and also the other way, like in hammer throw, and they get faster and faster. And when you throw it, you smash them against each other. So inside this tunnel, it's really filled with this high-tech equipment all around the tunnel over 27 kilometers. And inside this tube, you speed up the beams of protons to near the speed of light and smash them against each other. So when you smash them against each other, you are really doing the Big Bang. Well, of course, not quite. We are not making the universe. So it's a little bang. And at this little bang, a lot of things would come out of it. And you would like to collect them all. To collect them all, you also need to build a very sophisticated and big device. What you see here is this is the device that would collect everything that's produced by the little bang. Compared to that, you can see the size of the human beings. And every time you draw a human being, you're supposed to draw one man and one woman, and one man and one woman down there. So this experiment is called Atlas. And they actually created a fun movie before they even start building this incredible apparatus. And here we go. So you're smashing protons against each other. Here's the little bang. A lot of things come out. And you're trying to observe all of them, collect them all, understand what's going on. And now you can tell what movie they had in mind. They made this little video. And they're really serious people. So they go this far to make sure to mimic this movie. But anyway, so after they started building this incredibly large apparatus, it looked like this. So you see the size of the man standing over here? So this empty area is now completely filled with more high-tech equipment, and you can appreciate the size of this instrument to measure everything that comes from this little bang. So the question then is, can we really make dark matter? So what you're doing here is smashing protons against protons. Proton is not a particularly heavy object among the zoo of microscopic particles we know of today. So it is like a tricycle. It's a fairly light object. But you try to speed the tricycle by pedaling on this like crazy. And once they attain incredible energies, you smash them against each other. Then what Einstein told us is that you can turn energy E into the mass m by E equals mc squared. So the energy of the tricycles, even though tricycles themselves are light, this energy can turn into mass like an airplane in a tank. But if the tank turns out to be dark matter, you don't see it. But you can still tell because you can observe the airplane going the other direction. If something going this direction, everything has to be balanced between left and right, above and below. So then you should be able to see something on the other end, but you don't see it, which means that you have created something that is invisible. And that's the way you try to look for the signature of the dark matter, which you might have made in this little bang. But so far, we haven't seen the evidence of that. Maybe this is actually a limitation of the experiments we are doing in Europe, because you're smashing protons against protons, and each time you do so, you get this incredible mess. Out of these so many things coming out from these little bands, what you're looking for is that one of these lines turns out to be invisible, and now you can tell that this is actually a really, really hard job. And you do this like every tens out of million billion times a year, and so that's what you're looking for. So maybe you can smash some simpler things against each other, because the proton the LHC experiment is smashing against is sort of like cherry pies. And when you throw them against each other, then all the goos of the pies would fly apart. And what you saw in the previous picture is the goo. But what you're really looking for is the cherry seeds inside these pies would go clink against each other. And that's the collision you're looking for that can make the dark matter. So if that's what you're looking for, it's probably a better idea to throw cherry seeds against cherry seeds. But you can immediately tell that throwing tiny things are hard, Making sure they meet is even harder. So this is a technology that didn't exist till about 10 years ago, but now there is. So there's actually plan to start building this kind of machine, hopefully in Japan, where I am today. And that idea is called International Linear Collider. So you again build the beam of the electrons. You first bring it to the end of this tunnel. And this is a linear accelerator. So it's a straight line, unlike the Large Hadron Collider, where beams are circulating inside this circular tunnel. And inside this yellow ring, yellow stuff, then you start to speed up the electrons on its way somewhere close to really close to the speed of light. And what you see, this strange picture, is that there's some structure inside where you can put the radio waves in. And radio wave is like wave in the ocean, where surfers can get sped up by the push from the waves coming towards the shore. So in the same way, you put the beams of electrons at a clever location where the wave can push you, and then the beams get faster and faster, and you squeeze them down to the incredible small size of only a few nanometers, about the thousandths of the thickness of the hair. You smash them against each other, then you can observe these collisions without the goo, very clean, and that's how we hope to see the signal of the dark matter eventually. And in addition to being able to meet dark matter this way, we hope, so that we can thank her, that dark matter would also tell us what the kind of universe she was born in, namely when the universe is less than a billionth of a second old. So meeting dark matter by itself is already very exciting, but the dark matter as a mother can tell us the environment she lived in, where she was born, how she got to here, when the universe was less than a billionth of a second old. So that's even more exciting. We get closer to the very beginning of the universe this way. And there are several things we are doing right now to understand even earlier moments of the universe, like studying the Higgs boson. But also another thing we are doing, trying to understand the issue of the antimatter. So let me first then talk about antimatter as my second topic beyond dark matter. So antimatter may sound like sci-fi, but it turns out you can make them. So these people are the first people who made the antimatter for the first time. So this is the first human-made picture of antimatter. They sent in powerful light called the gamma rays, and that photon, namely powerful light, turned into a pair of an electron, that's matter, and its antimatter counterpart called the positron. So electron is a matter particle that carries negative electric charge, and antimatter always has the opposite electric charge, which is positive. That's why this is called a positron. My home, Berkeley, is also the home to the birth of an antiproton. So while we are made of protons, you see, you have a lot of protons inside your body, but using this particle accelerator, they made antiproton. In this picture, antiproton is coming from above. You see the track of antiproton coming in. But when antiproton meets the ordinary proton, antimatter and matter would annihilate into pure energy. And that pure energy, again, equal mc squared, turn into the mass of various objects. That's why you see sort of spray of things coming out, which is called the star event. So you learned something already, namely that matter and antimatter are always created in pairs. But when they meet, matter and antimatter always annihilate in pairs back to pure energy. And Nobel Prize was awarded to discoverers of the antiproton here in Berkeley. And you actually see a lot of this antimatter at hospitals, which are used, for example, for the PET scan of your body for the cancer diagnosis. The PET scan stands for positron emission tomography, and positron is one of the antimatter products I mentioned just a minute ago. And antimatter sounds so sci-fi that indeed sci-fi movies use antimatter. For example, if you watch the movies of Star Trek, you have this spaceship called the Enterprise. And if you Google Enterprise, you see the design of their engine. Their engine runs on antimatter. Here's the design of the engine. It's very simple. Here's a storage unit of antimatter. All they have to do is to sprinkle this antimatter together with the rest of the matter inside this engine, and that produces tremendous amount of energy, which turns out to be 300 million times more efficient than regular gasoline. So small amount of antimatter can create a lot of energy. And that also showed up in another movie by Angels, called Angels Demons, starred by Tom Hanks. This is actually a novel written by Dan Brown, who also wrote the Da Vinci Code after this novel. And inside this story, a scientist at CERN, that's the European laboratory I talked about earlier, a scientist there produced a 1/4 gram of antimatter without the knowledge of the director general. And this 1/4 gram of antimatter would fall into the wrong hands. And don't actually be fooled. A 1/4 gram of antimatter doesn't sound much. It's sort of like a sugar cube. But if you let this 1/4 gram of antimatter annihilate with matter, the amount of energy that produces is actually as much as the atomic bomb in Hiroshima. So that's a lot of energy. And it's really amazing thing about this movie is that when the scientists made this 1/4 gram of antimatter, Director General Fabio Giannoli of the CERN today didn't notice it. Even though this scientist, in order to create this 1/4 gram of antimatter, must have spent the power bill as much as $1 billion, trillion. And Director General didn't notice. Look at what kind of budget they got at CERN, right? And as I said, this 1/4 gram of antimatter would lead to this tremendous explosion if it falls into the wrong hands. So what you learn, though, is that nobody pays this much power bill. So there's no danger that somebody can make this much antimatter and threaten us from explosion. So that's okay. So no human beings can make this much antimatter, but the Big Bang did. The Big Bang had a tremendous amount of energy. They created matter and antimatter. But as we learned already, when energy turns into matter and antimatter, they turn into 50-50 matter and antimatter. But if the universe stayed that way, eventually matter and antimatter meet with each other, and they annihilate 50-50, 1-to-1, then all of them would disappear, and universe would have been totally empty. Then you wouldn't be watching my talk today. So something must happen from the beginning of the universe to today. Somehow, somebody reshuffled the amount of matter and the antimatter, took one antimatter out of 1 billion, and managed to turn that into matter somehow. Now you have an imbalance between them, and all matter and antimatter pretty much meet and disappear 1-to-1, but this imbalance, 2 out of 1 billion, remains, and that's you. So this must be how we survive the Big Bang. So you survived at the expense of billion friends. So you should be very grateful to them. But of course, the key thing here is the who did it when to turn one antimatter out of billion to matter so that we could survive the Big Bang. So the best candidate we know today is actually neutrinos. So I told you that every matter particle has its antimatter counterpart, and electric charge of the matter is the opposite from the electric charge of the antimatter. Electron has a negative charge, positron has positive charge. You can never turn a negative charge to positive charge, so that would never happen. Proton has positive charge, antiproton has a negative charge. Again, positive doesn't turn into negative, so this would never happen. But there's only one kind of matter particles we know in nature that doesn't have electric charge, that is called the neutrinos. So neutrino has charge 0, therefore antineutrinos have charge -0, that's the same as 0. So in principle, neutrino may turn into antineutrino, or maybe antineutrino into neutrino. Then the neutrinos could have reshuffled the balance between matter and antimatter, as I showed you on the previous slide. So perhaps neutrinos protected us from the complete annihilation. That's a theory put forward by my friends Fukugira and Yanagira. So perhaps it was neutrinos who saved us from a complete annihilation during the Big Bang. To see if this was the right idea, the people are trying experiments to see if an antineutrino can turn into neutrino in some nuclear radio decay process. And we haven't found this yet. It is now known not to happen even once in a trillion years, but people are still looking. So let's see if the neutrino can turn into antineutrino. So that's one important ingredient. But also another thing we need is that neutrinos and antineutrinos should behave differently from each other, so that universe has a way of telling them apart from each other to choose matter over antimatter, so that we could survive, not anti-us, but we could survive the universe. And to tell whether neutrinos and antineutrinos can behave different from each other, there's now competing experiments going on. One in the United States, where they send a powerful beam of neutrinos made from accelerator, send them over 1,300 kilometers from Illinois to South Dakota, and trying to see if the neutrinos and antineutrinos behave differently from each other. And similar experiment is now being done in Japan by producing also powerful beam of neutrinos and send them to an experiment about 300 kilometers away. So this is much closer than the distance in the United States. And now the people are trying to increase the neutron production at this facility so that you can make something like 300 trillion neutrinos every second. And they're also building a new target for neutrinos, which is 8 times bigger. And so that you can have a better chance of observing neutrinos and antineutrinos and see if they behave different from each other with a large amount of data. And not only that, they are also doing these studies, they're also trying to study neutrinos coming from the sun and supernova and the cosmic ray interaction in the atmosphere. And it turns out that this direction heads towards Korea. So in the Korean peninsula, this beam of neutrinos goes above your head. So there's an even idea to build this kind of big detector, which is something like 100 meters high, 100 meters wide, somewhere in the mountain regions of the Korean peninsula, so you can see these neutrinos zooming by you, and that would actually give us better interpretation of what's going on, whether there's any difference between neutrinos and antineutrinos. So if that happens, there will be incredible collaboration between Korean scientists and Japanese scientists trying to see if the neutrinos really saved us from the complete annihilation. So anyway, that's a story about antimatter. And if this is the right story, after all these experiments, we learn something about what happened in the universe when the universe was only 10 to the minus 26 seconds old, which is a 100th of the trillionth of a second. That's how far back towards the Big Bang we can make in our journey towards understanding where we came from. Now, the last subject is really what's going on at the very beginning of the universe, called inflation. And that's the last and third subject of my talk today. So inflation is an idea that this entire universe we see, 13.8 billion light years across, was incredibly tiny at the beginning of the universe, which could sit on your palm. Not just on your palm, it's even smaller than the size of the atomic nucleus. So this microscopic, teeny tiny universe got stretched out by an explosive expansion called inflation to the macroscopic size we see today about the universe. So that's the idea of the inflation. And it sounds like a really crazy idea, but this crazy idea came from the observational evidence. If you look at, for example, the way galaxies exist in our universe today, and these galaxies actually based on real data, they got the real shapes and sizes and real colors. And you put those data into the computer and pretend that you're doing this flyby simulation based on the real data. Of course, don't try this home, because if you would like to do this flyby, you have to travel through space at a speed that's about 10 trillion times faster than the speed of light. So don't try that at home. But the basic message of this video here is that no matter how far away you go, the universe looks pretty much the same. No difference. Everywhere in the universe looks pretty much the same. So practically the same no matter how far you go. We talked about this too. By looking at the picture of the Big Bang, I told you that this difference in temperature is grossly exaggerated. It's actually very bland and boring. So this is actually very strange, right? Because if you do this experiment by trying to observe the light coming from Big Bang itself, by pointing your telescope to your right, then the light from the edge of the universe spent 13.8 billion years to reach us. So they just reached us. They didn't have time to go beyond us. But then how come the light come from the right edge of the universe has exactly the same temperature as the light coming from the left edge of the universe? They shouldn't have any time for them to communicate with each other. So how could they arrange themselves to have exactly the same temperature? So a friend of mine named Andre Linde came up with this analogy. So it's sort of like you're an explorer traveling around the globe and having discovered two remote islands in very different parts of the world. But if you visit those islands, the people there speak exactly the same language. Well, they are same at the level of 1 part in 100,000, so they even have the same accent. So if you see something like this, you don't have to be an anthropologist to come up with a theory that these people came from the same place. That's why they speak the same language with the same accent. So universe should be the same way too. That edge of the universe and the opposite end of the universe must have been together at some point. They should have talked to each other, and that's how they made sure they have the same temperature. And they got stretched out by this inflation. That's why they seem so far away from each other today. But because they remember they talked to each other back then, they still have the same temperature as they promised to each other 13.8 billion years ago. So that's the way we understand why universe looks so much the same every direction you look, everywhere you go. So that's the idea of this inflation. And only after the inflation, this incredible energy that stretched out the universe turned into the heat. And then the matter and antimatter were born, which eventually got reshuffled a little bit by neutrinos, maybe. But we cannot observe this directly, as I mentioned earlier, because this is the wall you can't see through. So no telescope can see beyond that point. But now we have a new tool. You might have heard of this idea. There's something called the gravitational wave. That is the ripple of space-time, which interacts so weakly, even through this dense fog of Big Bang. So you might be able to see the gravitational wave punching through this thick fog all the way through and traveling directly from the inflation to us. And what's going on in inflation is that universe is so tiny, and in tiny, tiny universe, the physics laws of physics of the microscopic world would be in action. And laws of physics in microscopic world is called quantum mechanics. And you hear a lot about quantum information, quantum computer these days. It is that quantum. And quantum mechanics tells us that everything is a little shaky, what's called the uncertain principle. So during the inflation, universe was pretty much empty, but not quite empty. It was also shaky too. So energy was bubbling in and out of this empty space. So the vacuum, what you think is nothing, was actually full of these energies. The vacuum was active. And this, the shaky energies during the inflation got now printed on the picture of the Big Bang we talked about, slightly hot spot and slightly cold spots. And these hot spots were nurtured by dark matter, as I mentioned earlier, which eventually grew to full-blown stars and galaxies, and eventually us. So this was an incredible stretch of the contrast by 15 order magnitude. That's like 1 trillion times a million. So these tiny, tiny, shaky universe in the quantum mechanics called the fluctuation became what we are today. So inflation planted seeds for the structure we see today. So that's why we say that dark matter is the mom that nurtured these seeds to a full-grown adults. But seeds had been planted by inflation, so inflation was our dad. So one takeaway message from today's lecture is that inflation is dad and dark matter is mom. So without either one of them, you wouldn't be here today. Of course, assuming that there was also neutrinos or superzero to save us from the complete annihilation at the same time. So that's the end of my story. So beyond dark matter, who is our mom, we eventually hope to really see if inflation really took place at the very beginning of the universe, because when the inflation was happening, everything was getting so stretched out so quickly, even the space and time itself starts becoming shaky, and that shaky space-time is nothing but the gravitational wave, which we hope to detect by looking at the polarization of the light from the Big Bang. So I'm partly involved in this satellite project from the JAXA space agency in Japan called LIGHTBIRD, which are trying to observe this shaky space and time because of the inflation at the beginning of the universe. So that's the end of the story. So we talked about all these profound questions the physicists attending this workshop, PASCOS, are talking about. I focus on this question, where do you come from? But as you saw, it's also closely related to many other questions on this list, like what it's made of. Well, we came from dark matter. What is basic laws? How do we change neutrinos to antineutrinos? And how did the universe begin, like the inflation? So that's what we physicists do and discuss at this PASCOS conference to attack the mysteries of the universe. Thank you for your attention.
Thank you for the very nice and interesting talk. Is there any question? If you want to, if you have a question, you should please raise your hand. There's a raise your hand button, I think. So.
Yanis is raising his hand, even though
Okay,
he's a physicist, not general public. Yanis?
Go ahead.
Right. So thank you for this exciting talk. It's very
welcome.
Interesting. Hitoshi, you showed this cluster of galaxies going through each other, and we probably have a few of those pictures already. Now, the dark matter is on one side, is always on one side, and then I would expect the regular matter to oscillate around the center of the dark matter. Have we caught any clusters of galaxies being on the other side?
Yeah. So the people have also seen example of these colliding clusters of galaxies, where you see the oscillatory sort of the waves of dark matter being emitted away from the collision point. So there is actually data showing that kind of ripples of dark matter wave going through the space.
I was more interested to see whether the regular matter is on the other side of the blue. If there is any oscillatory behavior like that, it can give you a lot about the parameters.
Yeah, so I don't know if there's an observation of that sort. I haven't seen one myself, but for this picture, it's clear that there wasn't enough time for that to happen. So the baryon is now being dragged by dark matter. So it has to first catch up before it starts to oscillate in this gravitational potential from the dark matter. So clearly that hasn't happened yet.
Okay, thank you.
All right.
Okay. I think Hyunmin Lee raised the hand, right?
Sorry, I pressed wrong button.
Oh, okay. Hi,
nice to
Hyunmin.
meet you, Hitoshi.
Okay. Well, it's a good chance to give some question if you like. No, this is basically public talk, so you can ask any questions. Well, it should be related to this talk, but anyway.
Yeah, and I personally love to have questions. No questions?
Oh, yeah, there's one. Raise hand. Who is that? Oh,
Young.
Youngjun.
Not Yeonjun.
Yeah.
So thank you for a very nice talk. And I have a very stupid question. So you suggested neutrinos might have saved us from complete annihilation.
That's right.
Is neutrino the only legitimate possibility, or there are some other possibilities?
Yeah, so among the particles we know, the only matter particle that can change from matter to antimatter is the neutrino, because it doesn't have an electric charge. But there are other possibilities. If you use, for example, some composite particles, not elementary, we also know the neutron doesn't have electric charge. So some people are hoping to see the neutron can turn into anti-neutron. And another particle, which is not a matter particle, but may play the role, is the Higgs boson. So when Higgs boson, I didn't have time to talk about this today, but if Higgs boson made a phase transition from sort of the gas phase in the early universe into the frozen solid phase, which is the universe today, then that phase transition was such a dramatic process that the gas turned into solid in the universe as a whole, then that could have also created some violent reactions that would reshuffle the amount of matter and antimatter. So these are some of the main ideas people talk about. We don't know which one is right. That's why we have to take the data, and hopefully people in Korea do decide to detect neutrinos coming from Japan as an ultimate international collaboration of some sort.
Thank you.
All right.
Actually, I have it can be a stupid, but a question.
No questions are stupid.
Yeah. What is your thought about listen to this alternative explanation of our standard cosmology that they just say it's basically the different model of gravity they need? Well, mostly I think this astronomy people and more on the general relativity people kind of suggest the idea of modified gravity or some different ideas that some of them actually claim there's no dark matter or no dark energy or so on. Do you think there's any chance that it's true or not?
For dark matter, trying to replace the evidence of dark matter by changing the laws of gravity is very difficult. And I'm not a super expert on this, so I can't vouch for it. But my understanding is that you have to tweak a lot of data to make sure that this idea of modified gravity explains all the evidence we have seen of dark matter. Because now we see evidence for dark matter on the scale of galaxy size to cluster of galaxy size. They even on the cosmological distances, all the way looking back at the surface of the Big Bang, and trying to accommodate all of this data by modifying gravity is not an easy thing to do for sure, maybe nearly impossible. On the case of dark energy, maybe there's a little more room to come up with an idea of modifying gravity to explain apparently speeding up expansion of the universe today. That's what the data says. That's why we came up with the idea of dark energy. Maybe there's still something going on there on the gravity side. So that is certainly something we should look further into. But all the attempts people made so far, again, to replace dark energy by a modified gravity has got into problems. And the recent observation of the merger of neutron stars, which have been detected both by gravitational wave in various telescopes, suggests that many of these theories are actually against the data now. So that's where things are, to my understanding.
Okay. There's a question, hand up from Gagan.
Oh, Dima.
Yes.
Hey, Dima. Gagan, you first,
yes.
okay?
Right. It's a very nice talk, so thank you. The way I sort of appreciated the talk, the theme and, the dark matter, antimatter, and the inflation. And basically, ILC more as an instrument, when you compare with LSC as a better instrument, let's say, for the dark matter side, and the hyper K, and then the Korean extension of that for the antimatter part, the neutrino sector, and also the inflation for this satellite-based experiment. So the question I have is that using ILC as an instrument, can we shed some light on the later two part, on the inflation as well as the antimatter side? Dark matter part is all clear that you have already said, but about the antimatter, maybe what you answered to Young-Jun. So can you please tell something about?
So definitely. So I actually have a recent paper with my students that the IOC can do a very good job in studying this antimatter question too. So the idea is that IOC is now tuned to produce a bunch of the Higgs bosons, but Higgs boson might actually decay into the mirror world. There's some kind of copy of the standard model. And in that copy of the standard model, anti-neutron, and also dark neutron, could be the dark matter of the universe. So in that case, Higgs boson you can produce ends up decaying into these particles in this mirror standard model, which may further decay back to the standard model particles with a very low energy collimated tracks. And that would lead to rather exotic decay of the Higgs boson, which can be studied with a sensitivity 4 orders of magnitude better than the LHC can. So that's the way you can see that Higgs boson is now communicating with another world somehow, which may be the origin of dark matter and also antimatter in this model. So that's where the IOC can do a very good job to understand this antimatter problem. There's even speculation that Higgs boson itself drove the inflation at the beginning of the universe. It's hard to prove that experimentally, unfortunately, but maybe by studying the Higgs boson much more with higher precision, we get some hint of that.
Thank you. Thank you very much.
Okay, Dima, my old friend.
Hitoshi, hello. Thanks so much for such a wonderful talk. It's really,
Thank you.
Really inspiring. Since this is a general talk, I have a question for you about yeah, you know, maybe a bit unusual for a physics talk.
Fire up.
I would like you to please comment on a bit on the sociology in science, and what I mean here is in your memory and mine. For instance, when the evidence for dark energy first appeared, people were extremely skeptical. They said, "Oh, how can you say that supernova that we don't understand can be used as standard candles when we?" And there was a lot of opposition to this idea. And then one day, the whole opinion pendulum swung, whoops, and then there was a Nobel Prize and whatnot. So the question is, can you comment on the sort of? I wonder because, for instance, dark matter. We have so many interesting sort of evidence about this, but we still don't know what it is. But still, people have strong opinions. And for instance, you just expressed one against basically modified gravity. So how much of sort of this opinions on sociology is how much role does this play in modern physics? That's my question.
Yeah, I think it does play some role in that, not just the modern physics, but also going back to the era of Galileo and Newton and Einstein and so on. And as the famous story that Einstein didn't believe the consequence of his own theory of gravity, that black holes exist and universe had a beginning. He didn't believe the consequence of his own equation and tried to even modify it. So the sociology and prejudice do play a role in the world of scientists, even in a genius like Einstein. So we know that as a fact. In the case of dark energy, certainly there was a lot of skepticism, but I would say that it was accepted much more quickly as it could have been otherwise, because of their other indications dark energy had to exist. So two of them are, in addition to the supernova data, or first, there are stars in our own galaxy in globular clusters, which seem to be older than something like 12 billion years. But estimate of the age of the universe around back then was only like 10 billion years. So how can stars be older than the universe itself? That sounds like a crazy idea. And it turned out that estimate of the age of the universe was done without knowing that the universe was speeding up. But once you know it, then if you go back in time, universe expanding more slowly earlier on. So the estimate of the age of the universe becomes longer. And then it grew up to like 14 billion. And now we say 13.8. So it solved one major puzzle about this. And another major puzzle that has to do with the Nobel Prize of Jim Peebles 2 years ago is the way dark matter nurture the stars and galaxies to grow, called the structure formation theory. And this theory predicted too much clumps in the universe compared to observation. And again, dark energy came to rescue this, because when the universe is speeding up, then dark matter would have a hard time collecting stuff to build more galaxies. So no wonder there seem to be fewer clumps than you'd have otherwise predicted. So all of these things were explained at the same time by accepting dark energy. So that was actually the beginning that people started taking this idea more seriously. So supernova data alone, I'm sure, wouldn't have done it. But because of the other things, people start to buy into this actually fairly quickly than that they would have otherwise.
Thanks so much. Yeah.
All right. Thank you, Dima.
There is
Young
one
Min?
question here. Youngmin Lee.
Yes. Can you hear me?
Yes, I can.
Yeah. First, thank you for the talk. And during the talk, you showed the structure formation of the universe with and without the dark matter. You showed the structure formation of the universe with and without dark matter.
Right.
Yeah, but I think we don't know about the initial condition, such as the imbalance between matter and antimatter, and also about we don't know exactly about the inflation. So my question is that how did you simulate the result, and how much is it reliable in?
Yeah, you're right. We don't know the initial condition of the universe, but we need sort of the intermediate condition of the universe. And that is what we observed with this, the light coming from 13.8 billion years away from us using the telescope. And that's the light called cosmic micro background, as you know, not the rest of the audience maybe. And by using this picture, you know how universe was like at this moment when it was 380,000 years old. So from this point on, you can study how things change since that time. You may not know initial condition when universe was still doing inflation, but at least you know what it was already when it was 380,000 years old. So you start your simulation from that point on, and that's how you can understand the difference between the case with dark matter and without dark matter. Does that answer your question?
Yeah, so you mean that even from that moment, the existence of dark matter gives different results, right?
Exactly.
Okay, I see. Thank you.
Okay. Any other question or comment? If not,
I'm Hyunmin.
Okay. Yes.
So finally, I have a question. Thank you for your talk. I have a question about the recent measurement, direct measurement of the Hubble parameter, Hubble constant. Can you comment on that?
Yeah, you know, I don't have a very clear opinions about this. So what Hyunmin is referring to is that when you measure how quickly the universe is expanding today, there are basically two main ways of doing so, and they seem to disagree with each other. But one way is actually measurement based on rather recent universe. The other way is based on more or less the universe when it was only 380,000 years old. So maybe the way the expansion speed changed from these earlier moments to today have some other ingredients we are not aware of, like extra high energy particles in the universe. And that's one idea that has been proposed to reconcile these two different measurements. And that might mean that there are more particles beyond what we know, for example, like axion. And certainly I do occasionally think about that. But the first thing we really need to understand is if there are any issues about the measurement itself, and that requires a lot more scrutiny than it had been done so far. So the situation is getting probably more serious than it was like a few years ago. So we should pay good attention to that. But I don't think it's still too early to jump on the conclusion that there is really something new, like axions beyond the other particles we know. But of course, if that turns out to be right, that's of course hugely exciting. So I'm watching carefully, but I don't have a very clear idea on what it should mean, what it actually has to be yet.
Okay, thank you.
Thank you, Hyunmin.
Okay, any more questions? Okay. If there's no other question, let's thanks to Hitoshi again. It was really interesting talk.
All right. Thank you for listening to me.